In this video, we're going to cover the second part of general chemistry. So this is a multiple choice video. It's full of multiple choice problems. And first, we're going to talk about chemical kinetics, how to write the rate law expression, how to find the rate constant K, the reaction mechanism problems, how to solve problems associated with zero order, first order, and second order reactions. And then we'll move on to nuclear chemistry. We're going to talk about how to find the missing element, how to calculate the nuclear binding energy, how to also solve half-life problems as well. And then we'll move on to chemical equilibrium, the Chatelier's principle. We're going to talk about what's going to happen if we increase the concentration of the reactants or the products. Will the reaction shift to the right or will it shift to the left? What's going to happen if we change the pressure, the volume, the temperature of an endothermic reaction? How will that affect the equilibrium constant K? We're going to cover all of those things. And then we'll move on to acids and bases. We're going to talk about how to find the pH of a strong acid, strong base, weak acid, weak base, buffer, solution, and also how to find the pH of the solution before, after, and during a titration. For equilibrium, we're also going to go over ice tables and how to solve those type of problems with quadratic formulas. And then we'll move on to KSB. We're going to talk about how to calculate the KSB and also how to find the molar solubility both in moles per liter and in grams per liter. We're also going to deal with a few Le Chatelier's principal problems associated with KSB. So if you increase the concentration of the product, will the solubility of the compound increase or decrease? And how will that affect the pH of the solution? So we're going to go into that as well. And then we'll move on into thermodynamics. We're going to talk about delta G, delta H, delta S, Gibbs free energy, entropy, how to calculate them, both under standard and non-standard conditions. And then we'll move on to electrochemistry. We're going to talk about how to find the cell potential, both under standard and non-standard conditions. We're going to talk about how to find the oxidizing and reducing agent, how to balance redox reactions under acidic and basic conditions, and also electrolysis problems, like how to find the mass that was deposited on a cathode if you're given the electric current and the time that it passed through the solution, and also how to calculate the electric current if you're given the amount of mass that was plated onto the cathode. So we're going to go over all of those things, and so let's begin. Let's jump right into it, and let's start with number one. Number one, the average rate of appearance of NH3 is 0.215 molar per second. Determine the average rate of disappearance of H2. So for this problem, feel free to pause the video and try it yourself and then unpause it, check the answers, and see if you got it right. So let's begin. Let's start with 0.215 m for NH3 per second. Now, molarity and moles are proportional if the volume is the same. And H2 and NH3, they're going to be in the same reaction vessel. So therefore, the volume, or the liters, is going to be the same. So we can use a molar ratio, but with molarity instead. So for every 3 moles of H2 that reacts or disappears, 2 moles of NH3 will appear. So we can put 2m for NH3 and 3m for H2. So it's a 3-to-2 ratio, and the molarity for NH3 will cancel. So to find the answer, it's going to be 0.215 times 3 over 2. And that's about 0.323. Now, is it going to be positive or is it going to be negative? Well, we know the answer has to be negative. It has to be B. The reason why it's negative is because the concentration of H2 is decreasing. Hydrogen gas is on the reactant side, and as the reaction goes from the left to the right side, the reactants will decrease the concentration, so they will disappear, and that's why we have a negative sign. If we were calculating the rate of appearance for NH3, it would be positive, because the concentration of NH3 is increasing as the reaction goes from the left to the right. Number 2, which of the statements shown below is correct given the following rate law expression? Is it A, B, C, or D? Let's find out. So all we got to do for this problem is plug in the numbers. For anything that is constant, we're going to plug in a 1. For anything that changes, we'll plug in the respective value. So for A, the rate of the reaction doubles as the concentration of A doubles. So what we're going to do is we're going to plug in a 1 for K, it's a constant. We're going to put a 2 for A because it doubles. B is a constant, so we're going to substitute 1 for that. And the same is true for C. So 2 squared is 4. So the rate should increase by a factor of 4. So A is a false statement. The rate doesn't double. B, the rate of the reaction decreases by half as the concentration of C doubles. True or false? Well, let's find out. So rate is going to equal K. Well, we're going to put a 1 for K. A is going to be 1. B is 1 as well. And for C, we're going to plug in 2, but it's raised to the 0 power. Anything raised to the 0 power is 1. So if the rate is equal to 1, that means that it doesn't change. It remains the same. So B is eliminated. C, the rate increases by a factor of 3 as the concentration triples in value. So rate is going to equal 1 for K. We don't have to put 1 for A or C because it's going to be the same. But we can plug in 3 for B. And B is raised to the first power. So 3 to the 1 is equal to 3. So C is a true statement. C is the answer. But now let's check the last statement. The rate of the reaction increases by a factor of 4 as the concentration of B and C increases by a factor of 2 simultaneously. So rate is equal to, we're going to put 1 for K. A stays the same. And B increases by a factor of 2. And C increases by a factor of 2. But C is raised to the 0 power. Anything raised to the 0 power is 1. So this is going to be 2 times 1, which is equal to 2. So the rate will not increase by a factor of 4 if we double the concentration of A and B. In fact, the rate increases by a factor of 2. So D is eliminated. And therefore C is the right answer for this problem. Number 3. Use the following experimental data to determine the rate law expression and the rate constant K for the following chemical equation. So we're going to find the rate law expression 2 ways. We're going to do it the fast way conceptually, and then we're going to actually use an equation. We're going to write it out. So pick 2 trials in which the concentration of O2 is constant and the concentration of NO changes. We're going to find the rate order for NO first. So this is trial 1, 2, and 3. If we pick trials 1 and 2, notice that the concentration of NO, it doubles from 0.1 to 0.2. It's not constant. The concentration for O2 is constant, though. It remains 0.1 for the first 2 trials. So by choosing trials 1 and 2, we can find the rate order for NO. And as the concentration doubles from 0.1 to 0.2, notice the effect that it has on the reaction rate. The rate increases by a factor of 4, from 1.25 to 5. 5 divided by 1.25 is 4. So therefore, 2 to the x is equal to 4. If 2 to the x is equal to 4, what is the value of x? We know that 2 squared is 4, so x has to equal 2. 2 squared means 2 times 2, which is 4. So therefore, in the rate law expression, the exponent of reactant NO is going to be 2. So it's second order with respect to NO. So now, let's find the order for O2. Pick 2 trials in which the concentration of NO is constant, but the concentration of O2 is not. So we're going to have to pick trials 1 and 3. In those 2 trials, NO has a constant value of 0.1. But the concentration of O2 it doubles from 0.1 to 0.2. And as that occurs, notice the effect on the reaction rate. It doubles from 1.25 to 2.5. 2.5 divided by 1.25 is 2. So the equation that we need to write is 2 to the y, we're using y for a different variable, is equal to 2 because the rate doubles. So what is the value of y? Whenever there isn't an exponent, it's always assumed to be a 1. So since the 2's are the same, that means that y is equal to 1. 2 to the first power is 2. So what this tells us is that it's first order for O2. So let's put a 1 here. So this is the rate law expression. Rate is equal to K times NO squared times O2 to the first power. And the only answer that has that option is answer choice D. So we know D has to be the correct answer. So let's find out if there's another way that we can get the answer, because maybe you don't see it conceptually. Maybe you prefer to use equations. So we're still going to use the first two trials to find the order for NO. So the way we can write the equation, it's going to be like this. Rate for trial 2 divided by the rate for trial 1 is equal to the concentration of NO raised to the x power, and then the concentration of O2 raised to the y power, divided by NO raised to the x, and O2 raised to the y. You can write it this way, but another way you can write it, which I actually think might be easier now that I'm doing this problem, let's write it like this. NO2 and NO1. It's really NO, but the 2 means like for trial 2. And then raised to the x power. And then here we're going to have O2 over O2. This is for trial 2, that's for trial 1. And that's going to be raised to the y. So the rate for trial 2, it's 5 times 10 to the minus 4. And for trial 1, the rate is 1.25 times 10 to the minus 4. The value for NO2, for trial 2, it's 0.2. And for trial 1, it's 0.1. And that should be raised to the x power. Now, the rate of O2 for trial 2, it's 0.1. And for trial 1, it's 0.1, so it cancels. So this cancels out to 1. 1 raised to the y is just 1. So we don't have to worry about it anymore. Now on the left side, the 10 to the negative 4 cancels when we divide them. So 5 divided by 1.25 is 4. And 0.2 divided by 0.1 is 2. So we get 2 raised to the x. Now, if you're having trouble figuring out what x is going to be equal to log 4 divided by log 2. Let me separate those two equations. So that's how you can find x, and then x is going to equal 2. So if you want to see why it works that way, let me first make some space. So let's say if we have 4 is equal to 2 to the x, the first thing you need to do is take the log of both sides. So log 4 is equal to log 2 raised to the x. A property of logs allows you to move the x to the front. Now for this problem, we really don't need to use logs, but in the case that you do need to use it, let's say if you can't figure out what the exponent is, this is what you can do to figure it out. So now we could divide both sides by log 2. So log 4 divided by log 2 is equal to x, which we know it to be 2. So you can type it in your calculator. Whenever you don't see a base for log, the base is always assumed to be 10, by the way. So we know it's second order for NO. So now let's use the same equation, but for O2. So we have to use trials 3 and 1. So the rate for trial 3 divided by the rate for trial 1 is equal to the concentration of NO raised to the x, which we know it to be 2, times the concentration of O2, this should be a 3, for trial 3. And then raised to the y. So let's plug in the numbers that we have. So R3, the rate for trial 3 is 2.5 times 10 to the minus 4. And for R1, it's 1.25 times 10 to the minus 4. For NO, we know it's going to cancel, but I'm going to write it anyway. So it's going to be 0.1 over 0.1 raised to the x, which is going to be 1 to the x, which is just 1. And then for O2, it's going to be 0.2 divided by 0.1 raised to the y power. So on the left, the 10 to the negative 4s will cancel because they're the same. 2.5 divided by 1.25, if you type that in your calculator, you should get 2. Now this cancels to 1. And then 0.2 divided by 0.1 is 2, but raised to the y. So we know that y is 1, but using logs, it's going to be like log 2 over log 2, which is 1. So therefore, we have the rate expression. Which is rate is equal to K times NO squared times O2 raised to the first power, which we don't have to put the 1 there. So it's second order for NO, first order for O2, but third order overall. You add it, 2 plus 1 is 3. So now let's calculate the value of K. So we can use any trial. It's easier to use trial 1 because 1 is easier to deal with than 2. So let's plug in the information for trial 1. So we're going to use this. So the rate is equal to 1.25 times 10 to the minus 4. And then for trial 1, the value of NO is 0.1 squared, and the value of O2 is 0.1. So 0.1 squared times 0.1, that's equal to 0.001 times K. So we need to divide both sides by 0.001. So 1.25 times 10 to the minus 4 divided by 0.001 is equal to 0.125, which we could see D is the correct answer. It has the correct rate law expression and the correct value for K. So that's it. That's all you got to do for this problem. Number 4. Which of the following will give a straight line plot in the graph of ln A versus time? Is it A, a zero order reaction, B, a first order reaction, or a second order or third order reaction? Now, to answer this question, you need to know the equations that are associated with chemical kinetics. So this is a good time to go over it. So first we have a zero order reaction, and first order, and a second order reaction. So for a zero order reaction, the rate is equal to K. For a first order reaction, rate is equal to K times A, or A to the first power. For a second order reaction, rate is equal to K times A squared. Now, that's the rate law expression. You need to know that if you plot A versus T, or the concentration of A versus time, you're going to get a straight line graph if it's a zero order reaction. For a first order reaction, if you plot the natural log of the concentration of A versus time, it's going to be a straight line. And for a second order reaction, if you plot 1 divided by the concentration of A against time, that is going to give you a straight line plot. So the answer for this problem is B. You simply have to know that if you plot the natural log of A versus time, you'll get a straight line plot. Now there's some other things you need to know. For a zero order reaction, the slope is equal to negative K. For a first order reaction, the slope is also equal to negative K. But for a second order reaction, the slope is equal to positive K and not negative K. Now the last thing, or the next thing you need to know is the half-life equation. The half-life equation for a zero order reaction is the initial concentration of A divided by 2K, where K is the rate constant. For a first order reaction, the half-life, which is the time it takes for the substance to change by half, is the natural log of 2 divided by the rate constant K. And for a second order reaction, the half-life is equal to 1 over the rate constant times the initial concentration of A. Now there are some other things that you need to know in addition to that. And that is the straight line equation, which is in the form y equals mx plus b. So the straight line equation for a zero order reaction it's A final is equal to KT plus A initial. And notice how it's in the form y is equal to mx plus b. So as you can see, here we're plotting A versus t, or like y versus x. X is the time, so time is on the x-axis, and the concentration of A, which is going to be on the y-axis. The slope is equal to positive k, and the y-intercept is A initial. B is the y-intercept for any straight line equation. But for a zero order reaction, the y-intercept is the initial concentration of A. Now, for a first order equation, it looks very similar, but it involves the use of natural logs. So the natural log of A is equal to, oh, by the way, this should be negative KT. I forgot the negative sign. The slope is equal to negative K. So ln A is equal to negative KT. The negative means that the concentration of A is decreasing over time. So it's negative KT plus the natural log of A initial, or the initial concentration of A. Now, for a second order reaction, the equation that you need looks like this. It's 1 over A final, I'll put F of final, is equal to positive KT plus 1 over A initial. So the reason why we have a positive slope is because as A decreases, 1 over A increases. Whenever you increase the denominator of a fraction, the value, well, whenever you decrease the denominator of a fraction, the value of the fraction increases. So that's why we have a positive slope in this case, because it's the reciprocal of A. So those are the equations that you need to know for chemical kinetics. But the answer to this problem is answer choice B. A first order reaction will give you a straight line plot if you were to graph the natural log of the concentration of A versus time. Number 5. Which of the following units of the rate constant K correspond to a first order reaction? Is it A, B, C, or D? So in the first order reaction, we have the rate law expression rate is equal to K times the concentration of A raised to the first order. So overall, it has to be first order. So let's solve for the units of K. So the rate is usually molarity divided by seconds. It's concentration over time, or the change in concentration over the change in time. So that's it has the units m over s. And A, it's going to be just m. So A is going to be, since A is a form of concentration, is measured in molarity. So to solve for K, we're going to multiply both sides by 1 over m. So here, m cancels, and the same is true on this side. So for a first order reaction, we have 1 over s, which is the same as s to the minus 1. Now for any order, you can solve it the same way, but here's some things that you need to know. For a zero order reaction, the units will be m to the first power, s to the minus 1. Now the time could be minutes, it can be hours, but it's always going to be to the negative 1. It shouldn't be -2 or -3. So for a first order reaction, it's going to be m to the 0, s to the minus 1, or which is the same as s to the minus 1. For a second order reaction, it's m to the minus 1, s to the minus 1. For a third order reaction, it's m to the minus 2, s to the minus 1. Do you see a pattern here? Notice that as the order increases, the exponents for m decreases by 1. However, for time, it doesn't change. It's always going to be to the negative 1 power. But keep in mind, it doesn't have to be s. It could be minutes, it can be hours, it can be days, it can be years, but it's always time raised to the negative 1. So if you want to write a general equation that you can just plug in and get the units is going to equal m raised to the 1 minus n, and then I'm going to put time raised to the negative 1, or t to the negative 1. So n is going to be the order of the reaction, the overall order. So let's say if we have a rate law expression that looks like this. It's k a squared b. So for b, it's first order, but overall, if you add the exponents, the overall order is it's third order overall. So we need to plug in 3 for n. So the units is going to be m 1 minus 3, and let's say the time is in minutes. Minutes to the negative 1. So it's going to be m to the minus 2 minutes to the minus 1. Let's try another example. So let's say if we have the rate law expression, rate is equal to k a squared b c to the third. So overall, the overall order is 6. So we're going to plug in n for 6, or replace n with 6. So it's going to be m 1 minus 6 s to the minus 1. Let's say the time is in seconds this time. So the units is going to be m to the minus 5 s to the minus 1. So in the case for our problem, use an equation, it was first order. So if we plug in 1 for n, it will be 1 minus 1 s to the minus 1. So 1 minus 1 is 0, so it's m to the 0 s minus 1. And anything raised to the 0 power is 1. So this is equal to s to the minus 1 for a first order reaction. So now you can find the units of k whenever you have the rate law expression. As long as you have the overall order of the reaction, you can now find the units of k. And just keep in mind that the time can change. It could be seconds, minutes, hours, days, years. So you have to look at the problem to figure out what the unit of time will be. So the right answer for this problem is answer choice B. Number 6. The initial concentration of a reactant is 0.453 for a zero order reaction. Calculate the final concentration of the reactant after 64.4 seconds if the rate constant K is 0.00137 m over s. So we went over the equation for this particular problem. And for a zero order reaction, the straight line equation is the concentration of A, or the final concentration of A, is equal to negative kT plus the initial concentration of A. So we can see that this is similar to y equals mx plus b. The slope is negative k. The y-intercept b is the initial concentration of A. So now all we need to do is plug in the information into this formula, and let's solve for the missing variable. So what are we looking for in this problem? So this question says calculate the final concentration. So we're looking for A final. K is given to us. It's negative 0.00, well, it's positive 0.00137, but there's a negative sign in front of it. And the time is 64.4 seconds. And the initial concentration is 0.453. By the way, when you look at this problem, make sure the units match. Notice that you have seconds for time and for K. So the seconds will cancel, giving you molarity. And this is in molarity, so that works out. So make sure your units match. If you see seconds and minutes, you may have to do a conversion. So now at this point, let's just plug in these numbers into the calculator. It's negative 0.00137 times 64.4. That's negative 0.08823. And we're going to add 0.453 to that value. The final answer should be 0.3648, which rounds to 0.365. So C is the right answer for this problem. Number 7. The initial concentration of a reactant is 0.738 m for a zero order reaction. The rate constant K is 0.0352 m per minute. Calculate the time it takes for the final concentration of the reactant to decrease to 0.255. So it's a zero order reaction again, so the equation is going to be the same. It's A final is equal to negative KT plus A initial. This time we can see that the final concentration is 0.255. K is positive 0.0352. We're looking for T, and A initial is 0.738. So first, let's subtract both sides by 0.738. We need to solve for T. So 0.255 minus 0.738, that's going to equal negative 0.483. And that's equal to negative 0.0352 T. So let's divide both sides by negative 0.0352. So these cancel. So if you type in negative 0.483 divided by negative 0.0352, you should get a time value of 13.72. And notice that K has unit minutes, so time is going to be in minutes as well. So B is the right answer for this problem. Number 8. Calculate the rate constant K for second order reaction if the half-life is 243 seconds. The initial concentration of the reactant is 0.325. The equation that we need is this one. Half-life is equal to 1 over the rate constant times the initial concentration. Now, we need to solve for K. So what we're going to do is we're going to multiply both sides by K, and at the same time we're going to divide it by 1 over the half-life. Let's see if I can fit it here. Ignore the equal sign. So if we multiply both sides by K and by 1 over T, notice that T cancels on the left side. But on the right side, K cancels. So the equation that we now have is K is equal to 1 over half-life times the initial concentration of A. So basically, K and T, they trade places. But for those of you who want to see how it happened, now you know. So now let's plug in the values that we have. So the half-life is 243 seconds, and the initial concentration is 0.325. So 243 times 0.325, that is equal to 78.975. So 1 divided by 78.975, you should get a final answer of 0.01266, which you can round that to 1.27 times 10 to the minus 2. As you move the decimal from left to right, if you move it 2 spaces to the right, that's where we get the negative 2 from. As you move it to the right, the exponent decreases by 2, the exponent of base 10. So the correct answer is answer choice D. We don't have to worry about the units because all of the units are the same. So that's it for this problem. Number 9, a reaction has a rate constant of 1.46 times 10 to the negative 3 s to the minus 1 at 298 Kelvin and 4.33 times 10 to the minus 2 s to the minus 1 at 421 Kelvin. Calculate the activation energy of this reaction. So the equation that you need for this problem is the activation energy is equal to R times natural log of K2 divided by K1, that's the two rate constants, over 1 over T1 minus 1 over T2. By the way, what is the order of this reaction? Is it first order, second order, zero order? Can you figure out based on this problem, based on the information that's given to you? Look at the units, s to the negative 1. Based on the units, you can tell what the order is. Now, the equation that I gave you, which was units, which is equal to m1 minus n s to the minus 1. So here we have s to the negative 1, m, 1 minus n, and then so forth. Notice that these two are the same, which means that if we divide both sides by s, we should get 1 is equal to m to the 1 minus n. And anything to the 0 power is 1, so 1 is the same as m to the 0. Since the bases are the same, the exponents must equal. So if you solve for n, you'll get n is 1. So anytime it's just s to the minus 1 without any molarity units, it's going to be a first order reaction. So those are some things to know. You can find the order of the reaction based on the units alone. So now let's actually finish this problem. Let's actually work through it. So this, the first value, 1.46, that is the value for K1. And the temperature, T1, is 298 Kelvin. K2 is 4.33, and T2 is 421 Kelvin, which corresponds to K2. Now R, you don't want to plug in 0.08206 for R. You need to use the energy constant, the 8.3145 joules per mole per Kelvin. And then it's going to be natural log K2 over K1. So K2 is 4.33 times 10 to the minus 2. And K1 is 1.46 times 10 to the minus 3. And that's a terrible looking 3. T1 is 298 Kelvin, and T2 is 421 Kelvin. Now, if you wish to type this in directly all at once in your calculator. Make sure you put parentheses in the bottom. Now, for those of you who like to do it step by step, I'm going to just do it that way just for you in this video. So let's start with the natural log. Let's type in ln 4.33 times 10 to the minus 2 divided by 1.46 times 10 to the minus 3. So you should get 3.3897. And then that number is multiplied by 8.3145, but we'll do that later. Now if you type in 1 over 298, that's about like 0.0033557. Subtract that by 1 over 421. You should get 0.0009804. So 3.3897 times 8.3145. That's about 28.1837. And then we're going to divide it by the number in the bottom. So you should get 28,747. But because R has the units joules per mole per Kelvin, EA, activation energy, is going to have the units joules per mole. The Kelvin unit cancels with the Kelvin temperatures on the bottom. But we need kilojoules per mole. So to convert from joules to kilojoules, divide by 1,000. So then you should get 28.7 kilojoules per mole. So D is the right answer. Number 10. Which of the following particles is equivalent to an electron? Is it A, B, C, or D? This is something you have to know. So the answer is A. A beta particle is the same as an electron. It has the symbol 0, negative 1, E. You can also write it as 0, minus 1 with a beta symbol. So the top number for nuclear chemistry is the mass number. And the bottom number is the charge. For an alpha particle can be written as 4,2 with a helium nucleus. You can also write 4,2 alpha with an alpha symbol. So an alpha particle has a mass of 4 and a charge of 2. A positron is the antiparticle of an electron, so you can write it as 0, 1 e. So it has a positive 1 charge, but it still has a mass of virtually 0, just like an electron. So it's different from a proton. You can also write it as 0, 1 with a beta symbol. A gamma particle is basically a very energetic light particle. So it has a mass of 0 and a charge of 0, and it has the gamma symbol. By the way, the symbol for a proton, it's 1, 1, p. A proton has a mass of 1 and a charge of plus 1. For a neutron, it's 1, 0, n. A neutron has a mass of 1, a charge of 0, because it's neutral. Neutrons and protons, their masses are approximately equivalent. But for this problem, answer choice A is the right answer. Number 11, identify the missing element. So for now, let's call it X. We need to find the mass and the atomic number. To find the mass number, we need to make sure that the equation is balanced. On the left side, the total mass is 226. On the right side, we have a mass of 4 for the alpha particle, and we need to find the missing mass. So 4 plus what number is 226, or 226 minus 4 is, we know to be 222. To find the missing atomic number, we can subtract 88 by 2, and we will get 86. Now, the atomic number is really the important number that we need here. That's going to identify the element. So if you go to the periodic table and look for which element has an atomic number of 86, it's radon. So the right answer is B. Number 12. The half-life of cesium-137 is 30 years. Calculate the rate constant K for the first order decomposition of isotope CS-137. So the equation that we need that connects half-life with the rate constant K is this equation. K is equal to the natural log of 2 divided by the half-life if it's a first order reaction. So we just have to plug this in the calculator. So ln 2 divided by 30 is equal to 0.0231 years to the minus 1. So the right answer for this problem is B. Number 13. The half-life of iodine-131 is about 8.03 days. How long will it take for a 200-gram sample to decay to 25? Most decay problems are usually first-order reaction problems. And we can figure out the answer conceptually. So starting with 200 grams, it's going to take 8.03 days to decay to 100 grams because that's the half-life, the time it takes to decay by half. So in another 8.03 days, we're going to have 50 grams of iodine 131 left over. And it's going to take another 8 days for it to go down to 25. So 8.03 times 3 is about 24.09 or 24.1 days. That's how you can find the total time. But now let's say if we want to use an equation to get the same answer. The equation that you could use is ln A final over A initial is equal to negative KT. You've seen this equation earlier in this video in this form. ln A final is equal to negative KT plus ln A initial. This is for a first order reaction. So let's plug in everything that we have and let's solve for T. So the final amount is 25 and the initial amount is 200. The units grams will cancel. Now, we don't know the value of K, but we got to find it. So we can use this equation. K is going to be ln 2 divided by half-life, which is 8.03 days. So ln 2 divided by 8.03, you should get 0.0863 2 for the value of K. So now we could plug it in into the equation. So now we need to solve for T. ln 25 divided by 200 is about negative 2.0794. And if you take that number and divide it by negative 0.08632, you should get the value for T. And you should get about the same answer, which is 24.1 days. So C is the right answer. So now 14. Which of the following shows the correct equilibrium expression for the reaction shown below? Now what you need to keep in mind is that any reactant or product in the liquid or solid phase should not be included in the expression for K. So we can eliminate copper oxide and copper because they're both in a solid phase. So A cannot be the right answer. The equilibrium constant K is equal to the ratio of the products divided by the reactants. And that is the concentration of the products and reactants. So H2O is the product, it's on the right side, and H2 is a reactant, it's on the left side. Now the coefficients of the balanced reaction will become the exponents of the equilibrium expression. So the reaction is already balanced. That means that there's a 1 in front of H2O and H2. So the exponents are 1 as well, respectively. So the correct answer for this problem is answer choice B. (15) Calculate Kp for the following reaction at 298 Kelvin. Kc is 2.41 times 10 to the minus 2. For this problem, you need to know the right equation to use. Kp is equal to Kc times RT raised to the n, or the change in n. Delta n is the sum of the products, or the sum of the coefficient of the products, minus the total sum of the reactant coefficients. So for the products, we have one methane molecule and one H2O molecule. So we have two product molecules. And for the reactant side, we have 3 hydrogen gas molecules and 1 carbon monoxide molecule. So there's 4 molecules on the left side. So delta N is 2 minus 4, which is negative 2. We have the value of Kc. We know it's 2.41 times 10 to the minus 2. And R is the gas constant, 0.08206. And the temperature is 298 Kelvin. And so we're going to raise that to the minus 2. So if you type in 0.08206 times 298, that's 24.45. And if you raise that to the negative 2, you should get 1.672 times 10 to the negative 3. And then we're going to multiply that number by 2.41 times 10 to the minus 2. So the final answer is equal to 4.03 times 10 to the minus 5. So answer choice C is the right answer. 16. Use the following information below to calculate the missing equilibrium constant of the net reaction. So we have to solve this problem as if we're doing the Hess law problem, but with equilibrium constants instead. So you need to know that if you double a reaction, like if you increase the coefficients by a factor of 2, the equilibrium constant will be changed not by a factor of 2, so it won't become 2k. In fact, it's going to become k squared. And if you multiply the coefficients by half, the equilibrium constant k will become k raised to the half. If you reverse it, it turns into 1 over k. So our goal is to get the equilibrium constant for the third reaction. So we need to focus on the right species. In the first reaction, let's call this number 1. Which species should we not focus on? Which reactants and products should we not focus on? Is it CO, C, or O2? You do not want to focus on any reactant or product that is found in both equation 1 and 2. You want to focus on the ones that is only found in equation 1 and not in equation 2. So oxygen is found in both equations 1 and 2, so we don't want to focus on oxygen. Carbon monoxide is found in equations 1 and 2, so we don't want to focus on that. If you do, it's going to make it harder to adjust the two equations such that they would add to the third equation. We want to focus on carbon. It's only found in equation 1, and we want to focus on CO2. It's only found in equation 2 and not in equation 1. So let's start with carbon. We have 2 carbons on the right side, but we need to match it so that it can look like equation 3. We only have 1 carbon on the left. So therefore, we need to reverse equation 1 and multiply by a factor of 1/2. So first, let's reverse it. Well, let's do it simultaneously. 2 times the half is 1, so we're going to have 1 carbon atom plus half of an oxygen molecule, and then we have two carbon monoxide molecules multiplied by half. This is going to turn into 1. So we're going to get 1 carbon monoxide molecule. So now, what is the effect on K1? Since we reversed it, it's going to be 1 over K1. And we multiply the coefficients by 1/2, so we're going to raise the exponent of K1 to 1/2. Now let's focus on equation 2. So we're going to focus on CO2. We have half of CO2 on the left, but we need 1 on the right. So we need to reverse it and multiply the equation by a factor of 2. So we're going to have 1 whole CO2 molecule on the left, and on the right, 1/4 times 2 is 1/2. Oh wait, we need to reverse it. I almost forgot about that. So we have to multiply by 2 and reverse it. So 1/4 of O2 times 2 is 1/2 of O2. And half of CO times 2 will give us 1 CO molecule. And half of CO2 times 2 is 1 CO2 molecule. So now, since we reverse it, it's going to be 1 over K2. But now, since we doubled the coefficient, we need to square K2 as well. So 1 over K2 squared. Now let's add these two reactions. Let's see if it's going to give us the net reaction. So notice that we have a carbon monoxide molecule on the right and 1 on the left, so they cancel. On the left we have 1 carbon atom. Now 1/2 O2 plus 1/2. 1/2 plus 1/2 is a whole. So we get 1 oxygen molecule and plus 1 CO2 molecule. The CO2 molecule just dropped down. So now, what is the equilibrium constant for the third reaction? Do we add 1 over K1 raised to the 1/2 plus 1 over K2 squared? Or do we do something else? Now, if it was Hess's law using enthalpy, we would add the enthalpy values. But because we're dealing with the equilibrium constant, we have to multiply them and not add. So it's going to be 1 over K1 raised to the 1/2 times K2 squared. So first, let's go ahead and make some space. So now let's plug in everything into that equation. So Kc is now equal to 1 divided by K1 is 0.143 raised to the 1/2. I converted the scientific notation into its standard value. And K2 is 0.0235 raised to the second power. So 0.0235 squared, that's like 5.52 times 10 to the minus 4. And if we multiply that by 0.143 raised to the 1/2, you should get 0.000208884. So 1 divided by that number is approximately 4788. So this rounds to about 4790. So D is the right answer. So that's how you can find the K value of a third equation using the first two equations. So just to review, let's say if you have this reaction A plus B and it converts into C, and let's say the equilibrium constant is just K. If you double the coefficients of the reaction, it will turn into K squared. If you multiply by 1/2, it's going to be K raised to the 1/2. And finally, if you reverse it, it's going to be 1 divided by K. And whenever you add two equations, it's going to be like K1 times K2. So if we have let's say D plus E and becomes F, let's call that K2. So if we add equations 1 and this equation, that will give us A plus B plus D plus E turns into C plus F. So the K value that's associated for that reaction is it's K1 times K2. It's the product of these K values. So make sure you understand that in case if you see it on your next exam or something. So that's it for this problem. Number 17. At equilibrium, the partial pressures of xenon, chlorine, and xenon tetrachloride were found to be 215, 315, and 723 millimeters of mercury, respectively. Calculate Kp. If you want to find the equilibrium constant, and if you have the equilibrium partial pressures or concentration values, you can simply plug it into the equation. You do not need an ice table. Only when you have initial values or initial concentration values, that's when you need an ice table to solve it. So let's write the expression for Kp. It's going to be products over reactants. So xenon tetrachloride is on the product side, and it has a coefficient of 1. So it's raised to the first power. Xenon is on the reactant side, and chlorine is also on the reactant side. But chlorine has a coefficient of 2, so it's going to be raised to the second power. So now all we need to do, because we have the partial pressures at equilibrium, we can plug in these numbers directly into this expression to get the value for Kp. So for xenon tetrachloride, it's going to be 723. And for xenon, it's 215. And for chlorine, it's 315 but squared. $315 squared is 99,225, and if you multiply that by 215, you should get this number on the bottom: 213,333,75. So 723 divided by 21,333,375. You should get 3.389 times 10 to the minus 5. So D is the right answer for this problem. 18. A reaction mixture initially contains 0.75 of HI. At equilibrium, the concentration of I2 was found to be 0.3. Calculate the equilibrium concentration of HI in the mixture. So we have initial concentration values and equilibrium concentration values. So we need an ice table. Now initially, we have 0.75 of HI. So that means that there's no hydrogen gas or iodine gas in the reaction chamber. Now at equilibrium, the concentration of I2 was found to be 0.3. So if we add the missing values, that means that iodine, if it went from 0 to 0.3, it increased by 0.3. And that means hydrogen gas must also increase by 0.3 because those two are in a 1-to-1 ratio. Now, if we look at iodine and HI, notice that it's a 1-to-2 ratio. So for every mole of iodine that's produced, 2 moles of HI reacts. So if the products are increasing, the reactants must be decreasing, but by twice the amount. So if 1 mole of iodine is produced, 2 moles of HI reacts. So if 0.3 moles of iodine is produced, 0.6 moles of HI reacts. And that's why we have negative 0.6, because it's decreasing. So the final concentration of HI is simply 0.75 minus 0.6, which is going to be 0.15. And for this problem, we don't need Kc. We could find Kc if we want to, using these three values, but the question only wanted the equilibrium concentration of HI in a mixture, and that's 0.15. So A is the right answer for this problem. 19. The partial pressures of dinitrogen oxide, or monoxide, oxygen gas, and dinitrogen tetroxide are currently 0.134, 0.265, and 0.483 atmospheres respectively. Determine if the reaction is at equilibrium or if it will shift to the right or to the left. So what we need to do is find Q, which is the reaction quotient, and compare it to K, the equilibrium constant. So if Q is greater than K, it's going to shift to the left. One way you can visualize it is you can put K on a number line and put Q to the right. Because Q is greater than K, it's going to shift towards K, so it shifts to the left. So now if Q is less than K, it's going to shift to the right. So if it's less than K, we need to put it on the left side. And since it wants to go wherever K is, it's going to move towards the right. Now the last thing we need to know is if Q is equal to K, the system is at equilibrium. So that's great, but how can we use this to find Q, the reaction quotient? We already have the value of K. We know that it's 56.8, but how can we find Q? Q can be found the same way as K. K is products over reactants, but you have to use the equilibrium concentration or partial pressure values. For Q, you have to use the initial concentration or partial pressure values. The partial pressure values that were given to us are not at equilibrium because it didn't state that it was at equilibrium. It says it's currently at 0.134, 0.265, and 0.483. So we're going to assume that those are initial values, unless if it's stated it's at equilibrium, which it will be no point for this problem. So Q, just like K, is going to be products over reactants, and the reaction is already balanced. So the only product that we have is N2O4, and it has a coefficient of 1, so it's raised to the first power. O2 has a coefficient of 1, but it's on the reactant side, so we're going to put it in the bottom. N2O has a coefficient of 2, so for this species, it's going to be squared. So let's plug in the values. So N2O4 has a value of 0.483. And for O2, the value is 0.265. And for N2O, it's 0.134 squared. So you can plug this in directly in your calculator. By the way, if you want to type it in all at once, just make sure to put the numbers in the bottom within one large parentheses. Otherwise, your calculator may divide by 0.265, but it may multiply by 0.134 squared, so you might get a different answer unless you put it in parentheses. By the way, you should be careful with that because that's where a lot of students make a mistake. Is when you have two things in your denominator, if you divide it without the parentheses, your calculator is going to divide by the first number and then multiply by the second, and a lot of students lose a lot of points because of that problem. So just make sure you enclose it in parentheses, and you'll get the right answer. So you don't want to lose points due to calculator errors. So the value that I got for this is 101.5 if I typed it in correctly. So now that we have Q, we need to compare it to K. So K is equal to 56.8 and Q is 101.5. So we can say that Q is greater than K. And because Q is greater than K, we know that it's going to shift to the left. So the correct answer for this problem is answer choice B. The reaction will shift to the left. Which of the following statements is correct? Let's look at A. The reaction shifts to the right if Q is greater than K. Is that true or false? Well, let's find out. So if we make a number line, let's put K in the middle. And since Q is greater than K, let's put it on the right side. If Q is greater than K, it's going to shift to the left. So A is a false statement. B. The reaction is product favored when K is significantly less than 1. Is that true or false? When K is significantly less than 1, let's say when it's like 0.001, it's reactant favored, not product favored. K is the ratio of products over reactants. For it to be product favored, we have to have a lot of products at equilibrium compared to the reactants. So let's say if we have 1,000 products to 1 reactant. This would be product favored. K would be very large. K would equal 1,000. But let's say if we have more reactants than products. Let's say if we have 1,000 more reactants than products. So it's reactant favored. Whenever the denominator of a fraction is very large, you're going to get a small value, like 0.001. Whenever the numerator of a fraction is very large, the value of the fraction is large as well. But since the denominator is very large, the value of the fraction is very small. And therefore, when K is very small, like 0.001, we can see that we have a lot more reactants than products, so it's reactant favored. So B is a false statement. Now what about part C? Increase in the temperature for an endothermic reaction causes the equilibrium constant K to decrease. Is that true or is that false? Let's find out. So let's say if we have a reaction, A plus B turns into C, and it's endothermic, so delta H is positive. What's going to happen if we increase the temperature of an endothermic reaction? Will the reaction shift to the right or will it shift to the left? For an endothermic reaction, you can treat delta H as if it's a reactant. Anytime you increase the concentration of a reactant, the reaction will shift to the right. According to Le Chatelier's principle, if you increase the concentration of the reactant, the system is going to try to decrease the concentration of that reactant. And the way it decreases it is it's going to shift the reaction to the right. As the reaction shifts to the right, the concentration of the products will go up, and the concentration of the reactants will go down. So that's how it brings the reactant back down to its equilibrium level, so to speak. So the same will be true. If we increase the temperature, we can treat delta H as if it's a reactant, and so the reaction is going to shift to the right. And anytime it shifts to the right, the concentration of the products will increase in value because it's going towards the products. And since the reaction is moving away from the reactants as it moves to the right, the concentration of the reactants go down. And since K is the ratio of products to reactants, K is going to increase in value. Since the products go up, the value of the fraction will increase. Anytime you increase the numerator of a fraction, the value of the entire fraction goes up. And the reactants, because they decrease in value, K will also increase in value. Whenever you decrease the value of the denominator, the value of the entire fraction also goes up. So increase in the products will increase K, the numerator increases. Decrease in the reactants will also increase K because the denominator decreases, which increases the whole value of the fraction. So K greatly increases when you increase the temperature. So C is a false statement. D. The presence of an inert gas has no effect on the equilibrium constant K. Is that true or false? By elimination, you know it has to be the right answer. So it's a true statement. If you were to add an inert gas to the system, because it's inert, that means it's non-reactive. It's not going to affect or react with the reactants or the products. And so it will not affect the equilibrium constant K. Also, K will not change if you change the reactants or the concentration of the products. And it will not change if you were to change the pressure or the volume of the reaction. The only way K will change is if you change the temperature. So, I just want to make this clarification. If you change the concentration of the reactants or products without changing the temperature, the equilibrium constant K will remain the same. It's going to stay constant. It is a constant to begin with. However, if you change the temperature, which will change the reactants and the products, that's the only case when the value of K will change, if it changes due to temperature. So make sure you remember that fact. K depends only on temperature, nothing else. 21. Which of the following is a weak acid? So to answer this question, you need to know the 6 common strong acids, which are HCl, HBr, HI, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid. Usually, if it's not one of these 6 common strong acids, it's safe to say that it's not a strong acid. So we can eliminate nitric acid, that's strong. Sulfuric acid is a strong acid, and HI is a strong acid. So B, HNO2, is the weak acid. 22. Which of the following salts will decrease the pH of an aqueous solution? Acids have low pH values, bases have high pH values. So we're looking for the acidic salt. Let's start with C, potassium chloride. So we have the K+ ion and the chloride ion. Alkali metal ions like sodium and potassium are neutral ions. When placed in an aqueous solution, they will not change the pH of the solution significantly. Now, chloride is the conjugate base of a strong acid, HCl. The stronger the acid, the weaker the conjugate base. HCl is such a strong acid that the conjugate base, the chloride ion, is so weak that it's considered to be neutral. So KCl is a neutral salt. If you put it in water, the pH will remain approximately 7. Now let's consider sodium fluoride. The sodium plus ion is an alkali metal ion, and so it's neutral. However, the fluoride ion is not neutral. HF is a weak acid. It's not a strong acid. So because HF is a weak acid, the conjugate base will be a relatively stronger base. So fluoride will be considered a basic salt, or a basic ion. If you put sodium fluoride in water, the pH will increase. It's going to be above 7 because the conjugate acid is a weak acid. So we can write basic, but we can still eliminate D. So what about answer choice A, sodium nitrite? Is it an acidic salt, basic salt, or a neutral salt? Well, the sodium ion is neutral, but the nitrite ion is a basic salt. And the reason for that is because HNO2 is a weak acid. Notice that both HF and HNO2 are weak acids. Therefore, the conjugate base fluoride and nitrite are basic ions. But because HCl is a strong acid, the conjugate base chloride is going to be a neutral ion. So A is eliminated. It's a basic salt. So by elimination, we know the answer is NH4Br. So we have two ions, NH4 plus, the ammonium ion, and a bromide ion. So let's start with bromide. Is bromide acidic, basic, or neutral? If it has a negative charge, it's rare that's going to be acidic. This is considered to be a neutral salt or neutral ion. HBr is a strong acid, so the conjugate base bromide is going to be neutral. Now NH4 plus, this is something you have to know. It's a weak acid. If you were to put NH4 plus in water, it's going to donate a proton to water, generate an H3O plus and NH3, the conjugate base. And this reaction is reversible. So as you can see, when you put NH4 plus in water, it generates H3O plus. So it increases the hydrogen ion concentration in water, thus making water more acidic, or making the solution more acidic rather, and so the pH will decrease. So NH4Br is considered to be an acidic salt. If you put it in water, the pH will decrease below 7, and so B is the right answer for this problem. 23. The pH of a solution is 3.78. Determine the H3O plus concentration. In order to determine the hydronium ion concentration, there is an equation that we need, and it's equal to 10 raised to the negative pH. So all we have to do is type in 10 raised to the negative 3.78 into our calculator. And you should get a concentration of 1.66 times 10 to the minus 4. So the right answer for this problem is answer choice C. 24. Calculate the pH of a 0.25 molar acetic acid solution. The Ka of acetic acid is 1.8 times 10 to the minus 5. So for this problem, you could use an ice table, or you can just use an equation. But let's start with an ice table. So we have a generic weak acid, which I'm going to write as HA, and when it reacts with water, it's going to generate H3O plus and the conjugate base A minus. So initially, we have 0.25 for the acid concentration. Because water is a liquid, we don't have to include it in the equilibrium expression for Ka. And initially, we have a concentration of 0 for H3O plus and for the conjugate base A minus. So this is going to increase by x, and this is going to be negative x. So we're going to have x, x, and 0.25 minus x. So when we write the expression for Ka, it's going to be products over reactants. So it's H3O plus times A minus divided by the concentration of HA. So therefore Ka is equal to x squared divided by 0.25 minus x. When Ka is significantly small, which it is, 10 to the minus 5, we could ignore this x value. So we can avoid using the quadratic equation. So let me make some space first. So the simplified expression that we now have is we have x squared divided by 0.25, and that's equal to Ka, which we can replace it with 1.8 times 10 to the minus 5. So let's put the Ka value over 1, and let's cross multiply. So 1 times x squared is x squared, and then 0.25 times 1.8 times 10 to the minus 5. That's about 4.5 times 10 to the negative 6. Now at this point, we can square root both sides. So x is about 2.12 times 10 to the minus 3. Now keep in mind, x represents the concentration of H3O plus. So therefore, we can now find a pH. So the pH is equal to negative log of the H3O plus concentration And so we can take this value and plug it in for H3O plus. So if you type in negative log of 2.12 times 10 to the minus 3, you're going to get an answer of about 2.67. So B is the right answer for this problem. By the way, if you're wondering if Ka is small enough such that we can neglect the value of x, test it out. Plug it back into the equation and see if the answer you get is very close to the true value of Ka. So let me give you an example. So the equation that we had was Ka is equal to x squared over 0.25 minus x. And the value of x that we calculated when we assumed that x was negligible was about 2.12 times 10 to the minus 3. So to see if that answer is valid, what we're going to do is we're going to take this x value and plug it in to the equation. So go ahead and type this in your calculator. So this is going to be 0.25 minus the value of x, 2.12 times 10 to the minus 3. And this is squared. So if you type in 2.12 times 10 to the minus 3 squared, and then divide that by 0.25 minus 2.12 times 10 to the minus 3, all in parentheses, you should get 1.813 times 10 to the minus 5. So notice that the answer is it's slightly different from the true value of Ka. The true value of Ka for this problem was 1.8 times 10 to the minus 5. So it really didn't deviate that much. Because they're close to each other, that means this is a good estimation of x, which means we made the right decision to neglect the value of x. Now, if this answer was significantly different from the true value of Ka, then that's an indication that you shouldn't neglect the value of x, and you may have to do a quadratic equation. So now you know how you can tell whether or not if you should neglect the value of x. Just plug it back in and see if the Ka value that you calculate is very close to the true value of Ka. 25. Calculate the pH of the solution made by dissolving 30.5 grams of sodium fluoride in enough water to make a 650 milliliter solution. The Ka of hydrofluoric acid is 6.8 times 10 to the negative 4. So go ahead and try this problem. Feel free to pause the video and then unpause it when you're ready to see the solution. Now, what you should not do in this problem is you don't want to use the equation Ka is equal to x squared over the acid minus x. The reason being is we don't have an acid dissolve in a solution. Instead, we have a base, or a basic salt, sodium fluoride. If we had HF dissolve in a solution, then we should use Ka. But because we have sodium fluoride, a base dissolve in a solution, we should use Kb instead. So first, let's write the reaction. Fluoride, when we dissolve sodium fluoride in water, sodium is going to be the specks of the ion, so we don't have to worry about it. Fluoride is going to react with water to produce HF and hydroxide. And it's reversible. HF is a weak acid. And so let's make our ice table. We need to find the initial concentration of fluoride. And we're given 30.5 grams, so let's convert that. So 30.5 grams of sodium fluoride over 1. Na has a molar mass of 23, and fluorine has a molar mass of 19. So the molar mass for NaF is 42 grams per 1 mole. And we need to convert it to molarity. So we need to divide by liters now that we have moles. To convert milliliters into liters, simply divide it by 1,000, or move the decimal 3 units to the left. So 650 milliliters is the same as 0.650 liters. So 30.5 divided by 42 and then take that result divided by 0.65, you should get a molarity of 1.117. So that's the initial concentration of the fluoride ion. And we're going to have 0 and 0. Now, because we have nothing on the right side, the reaction has to shift to the right. It can't shift to the left. If it were to go to the left, then we would get negative values for HF and hydroxide. So that's not possible. So because it shifts to the right initially, we're going to have positive X on the product side and negative X on the reactant side. So if we add the first two rows, we should get 1.117 minus X, and on the other side, X and X. So Kb is the ratio of the products over the reactants. So the products are HF and the concentration of hydroxide divided by the concentration of fluoride. We don't include water because it's a liquid. Liquids and solids, you should not include it in the equilibrium expression. Everything else is in the aqueous phase, which you can include that in the equilibrium expression. So in terms of X, Kb is equal to X squared divided by 1.117 minus X. Now notice that we don't have the value of Kb. Instead, we have the value of Ka. But we can find Kb from Ka. So let's go ahead and do that. But first, let's make some space. So Ka times Kb is equal to 1 times 10 to the minus 14. So that means that Kb is equal to 1 times 10 to the minus 14 divided by Ka, which is 6.8 times 10 to the minus 5. Or, I meant to say 4. So if we divide those two numbers, you should get a value for Kb, which is 1.471 times 10 to the minus 11. 10 to the negative 11 is very, very, very small. It's much smaller than 10 to negative 5. So if we can neglect X when Ka was 10 to negative 5, we can certainly ignore this X value if it's at very small, such like negative 11. That's extremely small. So let's plug in Kb and let's solve for X. So let's put this over 1 and let's cross multiply. So we're going to have X squared, which is equal to the Kb value, 1.471 times 10 to the minus 11. We're going to multiply that by 1.117, and you should get 1.643 times 10 to the minus 11. So now we're going to take the square root of both sides. So X is equal to 4.05 times 10 to negative 6. Now, because we calculated X from Kb, X represents the concentration of hydroxide and not H3O+. So therefore, we need to find the pH by finding the pOH first. pOH is negative log of hydroxide. So let's plug in the value of X for the hydroxide concentration in the pOH equation. So if you type in negative log of 4.05 times 10 to the minus 6, the pOH value is therefore equal to 5.39. So using pOH, we can now calculate the pH value. So we said pOH was 5.39. Now the pH plus the pOH, in an aqueous environment, these two numbers add up to 14. So therefore pH is equal to 14 minus pOH. So if you subtract 14 by 5.39, you'll get the pH value. And it turns out that it's 8.61. So therefore C is the right answer. Now it makes sense. Earlier in this video, we said sodium fluoride is a basic salt. The pH will be above 7, and it is. It's 8.61. If we were to add an acidic salt to water to make a solution, the pH would be less than 7. It could be like 5 to 6 somewhere, or maybe 4-ish. But in this case, it's 8.61. So that's the answer for this problem, and that's how you find it. So just keep in mind, look at the substance that is dissolved in water. If it's an acid, make sure you use Ka to find X, and X will represent H3O+. If it's a base, make sure you use Kb. Sometimes you may have to find Kb from Ka, but use Kb, and keep in mind that X represents hydroxide. So let's review the equations that we have. So let's say if you have an acid like HF is dissolved in water. So step 1, use this equation. Ka is equal to X squared divided by the acid concentration minus X. If Ka is very small, which is usually the case, you could ignore the X value. So if it's like 10 to negative 4 or less, it's safe to say that you could ignore X. If it's like 10 to the minus 2 or 10 to the minus 3, you have to make a decision. But if it's like 10 to the minus 2, I probably won't take a chance of ignoring X. I would try to use the quadratic equation. But once you use this equation and once you find X, you need to know that X represents the concentration of H3O+. So your next step is to find a pH, which is negative log of the H plus or H3O+ concentration. So that's if you have an acid dissolve in water. Now let's say if you have a base dissolved in water, like sodium fluoride. First, you need to use the Kb equation, which is X squared divided by the concentration of the base minus X. And if Kb is small, you could ignore the X on the bottom. Now, once you have X, keep in mind that for a base, X is equal to the hydroxide concentration and not the H3O+ concentration. So you got to find pOH by taking the negative log of the hydroxide concentration. And then you can find pH by subtracting 14 by pOH. And keep in mind, Ka times Kb is equal to 1 times 10 to the minus 14. So those are some equations that you need to know for the chapter on acids and bases. 26. A solution contains a mixture of 0.755 molar HF and 0.125 molar sodium fluoride. Calculate the pH of the solution. The Ka of hydrofluoric acid is 6.8 times 10 to the minus 4. So notice that we have the weak acid and its conjugate weak base. Together, they create a buffer solution. And to find the pH of a buffer solution, you can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log base divided by acid. So let's find the pKa first. pKa is equal to the negative log of the Ka value. And the Ka value is 6.8 times 10 to the minus 4. So if you type in negative log 6.8 times 10 to the minus 4, you should get a pKa value of 3.167. So now we can take that and plug it into the buffer equation. So it's going to be pH is equal to 3.167 plus log base over acid. So which one is the base? Well, the acid is the one that has more hydrogens. So HF is the acid and NaF is the base. So it's going to be 0.125 divided by the acid concentration, which is 0.755. So you can type this in directly into your calculator, just the way you see it. And if you do that, you should get, before I give you the answer, is the pH going to be greater than or less than the pKa value? What do you say? So, if we were to have equal amounts of acid and base, the pH will equal the pKa. So it would be 3.167. If we have more of the base, less of the acid, the pH will be above 3.167. And if we have more of the acid, less of the base, the pH will be below 3.167. Notice that we have more of the acid concentration. So therefore, the pH should be less than 3.167. And it is. If you type this in the calculator, you're going to get 2.39 because we have more of the conjugate acid and less of the conjugate base. And so D is the right answer for this problem. 27. Which of the following is a buffer solution? Is it A, B, C, or D? Now, keep in mind that a buffer solution is the combination of a weak acid and its conjugate weak base. So, let's look at answer choice A. HF is a weak acid, and HCN is a weak acid. We don't have any weak bases, so A is eliminated. If we look at C, HI is a strong acid, and KI is neutral. So we don't have a weak acid, weak base pair, so C is eliminated. Looking at B, HCl is a strong acid, and sodium chloride is neutral, so B is eliminated. Acetic acid is a weak acid, and sodium acetate is a weak base. And also, notice that acetic acid and the acetate differs by one hydrogen. So that means that it's a conjugate acid-base pair, which is a requirement for a buffer solution. So D is the right answer. 28. Which of the following is a Lewis acid? Is it borane, BH3? Is it aluminum chloride, AlCl3, or iron 3 chloride, FeCl3? Or is it all of the above? The correct answer is it's all of the above. If you were to draw the Lewis structure of BH3, if you add up the valence electrons, you'll see that it has 6 valence electrons, and boron likes to form 3 bonds. It's going to have an incomplete octet. So, because boron doesn't have 8 electrons, it's electron deficient, and so it can accept a pair of electrons. And Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. A bronzolari acid is a proton donor, and a bronzolari base is a proton acceptor. An arsenous acid is a substance that generates H plus or hydronium ions in solution. An arsenous base is something that generates hydroxide ions in solution. But BH3 is a Lewis acid. It can accept a pair of a pair of electrons. So let's say if we have a Lewis base like NH3, which has a lone pair. NH3 can donate a pair of electrons to BH3, and we're going to get this product, which looks like this. So as you can see, the nitrogen atom donated a pair of electrons, which makes it a Lewis base, or an electron pair donor. Boron was able to accept a pair of electrons, which makes it a Lewis acid, or electron pair acceptor. So as you can see, this bond that was created between the boron and the nitrogen atom, nitrogen provided the 2 electrons to generate that bond. So that's why nitrogen or ammonia is the Lewis base electron pair donor. And boron didn't provide any electrons to create that bond, so boron was the electron pair acceptor, or the Lewis acid. Now, aluminum chloride has a very similar geometry. It's trigonoplanar. And most trigonoplanar structures are usually Lewis acids because they can accept a pair of electrons. FeCl3 has a very similar structure. So all of these 3 compounds, they're very common Lewis acids. So D is the right answer. It's all of the above. 29. Write the equilibrium expression for KSP based on the following reaction. KSP stands for solubility product constant. Now there's different types of Ks. You've seen KC, which is the equilibrium concentration constant, and then there was Kp, which is equilibrium pressure constant, and Ka, the acid dissociation constant, Kb, the base dissociation constant. There's Kw, auto ionization constant of water. And if you see KEQ is just a generic equilibrium constant. So KSP works the same way as any type of K value. It's going to be products over reactants. So the products are calcium 2 plus and fluoride. Now the coefficient of fluoride is 2, so we need to square it. Now typically we would divide this by the reactant, but notice that the reactant is in a solid phase. So therefore we cannot or should not include it in the equilibrium expression. So we're going to put a 1 instead. So the right answer is answer choice B. It's the only one that matches what we have. And so that's how you can write the equilibrium expression for KSP, the solubility product constant. Number 30. Calculate the molar solubility of magnesium hydroxide. The KSP, or solubility product constant of magnesium hydroxide, is 1.8 times 10 to the minus 11. So, if we were to write an ICE table, this would be 0, 0, plus x plus 2x, because it's a 1 to 2 ratio. And for the left side, we can just put nothing there, or just a 1, because it's a solid. It's not going to be included in the equilibrium expression. And so for the last row, 0 plus x is x, 0 plus 2x is 2x. So if we were to write the expression for KSP, it's going to be the concentration of Mg2 plus multiplied by the concentration of hydroxide, but squared, since we have a coefficient of 2 in front of hydroxide. So the molar solubility of magnesium hydroxide is basically the value of x. It really represents the amount of magnesium hydroxide that is soluble. And so basically we want to find the concentration of MgOH2 that's in the aqueous phase. Notice that MgOH2 and Mg plus 2 is in a 1-to-1 ratio. And x represents the concentration of Mg plus 2. So if we could find x, we're going to have the concentration of Mg plus 2 that's dissolved in a solution, which is equal to the concentration of MgOH2 that's in the aqueous phase. So basically, anytime you need to calculate the molar solubility, you're looking for the value of x. So we can plug in 1.8 times 10 to the minus 11 for KSP. The Mg plus 2 concentration is the same as the value of x. Hydroxide is equal to 2x, but we have to square it. So 2x squared, 2x times 2x is 4x squared. And 4x squared times x is 4x cubed. So let's make some space first. So 1.8 times 10 to the minus 11 is equal to 4x cubed. The first thing we should do is divide both sides by 4. So 1.8 times 10 to the minus 11 divided by 4 is about 4.5 times 10 to the minus 12. And that's equal to x cubed. So to solve for x, you need to take the cube root of both sides. You can also write it this way. You can raise both sides to the 1/3 power. That's the same as taking the cube root. So whenever you raise one exponent to another, you multiply it. So 3 times 1/3, the 3's cancel, so you get x to the first power, which is x. And the cube root of 4.5 times 10 to the minus 12 is about 1.651 times 10 to the negative 4. So this is the molar solubility of magnesium hydroxide. So that's the amount of magnesium hydroxide that is dissolved in a solution. So the answer for this problem is answer choice A. 31. A saturated solution of lead 2 chloride contains 0.0159 m of Pb plus 2 and 0.0317 m of Cl minus. Calculate the solubility product constant of PbCl2. So, in this problem, notice that we have a saturated solution. That means that the system is at equilibrium. So we can simply plug in these values for Pb plus 2 and chloride, and that's going to give us the KSP value for lead 2 chloride. So let's write the expression of KSP first. So KSP is the ratio of products to reactants. So the products are Pb2 plus and chloride. Now we have a coefficient of 2 for chloride, so let's put a 2 in the exponent position. And we don't have to worry about the solid. We can put a 1 in the denominator if we want to. So let's plug in 0.0159 for the lead 2 plus concentration and 0.0317 for chloride. But don't forget to square it. So if you plug these numbers into your calculator, you should get 1.598 times 10 to the minus 5 for the KSP value of lead 2 chloride. So we can round that to 1.6. So C is the right answer for this problem. 32. For which of the following reactions is delta S, or the change in entropy, positive? Is it A, B, C, or D? Now, what you need to keep in mind is that gases have a very high entropy value. Entropy is associated with disorder, and gases are very disorderly. Solids. In a solid, the atoms are arranged in a nice, neat, orderly pattern. So solids have a very low entropy because they have a very low disorder among the crystal lattice. So they're very orderly. Now let's look at answer choice A. On the left side we have 3 gas molecules, and on the right side we have 2 gas molecules. So 3 gas molecules have more entropy than 2 gas molecules. So we're going from a high entropy system to a low entropy system. Whenever you go from high to low, the value is decreasing, so delta S is negative, not positive. So A is eliminated. Now let's look at answer choice B. We have a solid and a gas on the left and a solid on the right. Well, because the left side has a gas, the left side has a higher entropy than the right side. So we're going from high to low again. So anytime you go from high to low, the change in entropy is negative. So B is eliminated. Now looking at answer choice C, we're going from a gas to a liquid. A gas has more entropy than a liquid, so we're also going from high to low. So delta S is also negative. Now for D, we have 2 carbon atoms plus oxygen gas, and it turns into 2 carbon monoxide gas molecules. So we don't want to say it's 3 to 2 and assume that entropy is negative, because a solid, the entropy of a solid is very, very low compared to the entropy of a gas. In terms of numbers, the entropy of a solid could be like maybe 5, 10, or 20 joules per mole. Some of them could be 30 or 40. But the entropy of a gas could be like 200 joules per mole. So a gas is significantly higher in entropy relative to a solid. So when comparing a gas and a solid, you could ignore the solids, generally speaking. So on the left side we have 1 gas molecule, and on the right side we have 2 gas molecules. So we're going from a low entropy system to a high entropy system, so delta S is positive because the entropy is increasing as we go from left to right. So D is the right answer. 33. Calculate delta G, or the change in Gibbs free energy, using the following information at 340 Kelvin. So we're given the enthalpy value and the entropy value. So the change in enthalpy is negative, which means that it's an exothermic reaction. And the change in S, or entropy, is positive. So there's an equation that we can use to find delta G. And it looks like this. Delta G is equal to delta H minus T times delta S. Now notice that delta H is in kilojoules, but S is in joules. So for this equation to work, you have to convert joules into kilojoules. If you don't, you will not get the right answer, and that's important. You don't want to make this mistake on the exam. So let's plug in the numbers that we have. So delta H is negative 64.2 kilojoules per mole, minus the temperature, which is 340 Kelvin. Now we're going to convert 105 joules into kilojoules. So we can divide 105 by 1,000, or move the decimal point 3 units to the left. So it's going to be 0.105 kilojoules per mole per Kelvin. So the units Kelvin cancel, and we're left with kilojoules per mole and kilojoules per mole. So we can now add the two numbers. So negative 64.2 minus 340 times 0.105, you should get negative 99.9 kilojoules per mole. And so that's delta G. And because delta G is negative, the reaction, or this system, is spontaneous at 340 Kelvin. So B is the right answer for this problem. By the way, the video that you're currently watching is a 2-hour trailer version of a longer 7-hour video. This video currently has 40 multiple choice problems, but I'm going to post a link so you can access the remaining portion of this video, which contains a total of 150 multiple choice problems. So when you get a chance, feel free to check that out, and let's continue with the next problem. 34. Which of the conditions shown below will cause a reaction to be spontaneous for all temperatures? Is it A, B, C, or D? So let's make a table. We're going to have enthalpy, entropy, Gibbs free energy, and temperature. So this is going to be negative, positive, positive, negative. Well, let's make this positive, positive, and then negative, negative, and then negative, positive. It turns out that when both enthalpy and entropy is positive, delta G will be negative under high temperature conditions. When enthalpy is positive and entropy is negative, delta G will be positive under all temperature conditions. So at any temperature, delta G will be positive. Keep in mind, when delta G is positive, it's non-spontaneous. When it's negative, it's spontaneous, meaning the reaction will work. It will occur in the reaction or in the direction that it's given. When both delta H and delta S are negative, delta G will be negative only under low temperature conditions. And when enthalpy is negative and entropy is positive, delta G will be negative at any temperature. So, using this information, the reaction will be spontaneous at all temperatures if delta H is negative and delta S is positive. So that's answer choice B. Delta S is positive and delta H is negative. So B is the right answer. Now you might be wondering how you can get this information without committing this to memory. If you can commit this to memory, that's great, but we need to come up with a way to figure this out. So let's say delta H is about 10,000 joules per mole, or let's say 10 kilojoules per mole. And let's say delta S is about 0.1 kilojoules per mole per Kelvin. So H and S is going to be the same, but the only thing that's going to vary is the sign of H and S and the temperature. So we're going to plug in 10 for a low temperature value and 1,000 for a high temperature value. So let's prove the first case. So let's say that delta H is positive 10, and then we have a minus sign. We're going to plug in the high temperature value. So let's plug in 1,000 for a T, and delta S is 0.1. So this is 10 minus 100, which is going to be negative 90. So delta G is negative, which is true. So now let's plug in a low temperature. So H is still going to be positive 10, and then minus the low temperature, which we're going to plug in as 10, times the entropy value of 0.1. So 10 minus, let's see, 10 times 0.1 is 1, so we're going to get 9. And notice that it's positive. So delta G is positive at low temperatures when delta H and delta S are both positive. But when the temperature was high, like 1,000, delta G was negative, and this proved true. So when delta H and delta S are both positive, when the signs are the same, delta G is spontaneous only at high temperatures. At low temperature conditions, it's non-spontaneous. So now let's prove the second case. So it has to be non-spontaneous or positive at all temperatures, meaning if we plug in a low temperature or high temperature value, it has to remain positive. So let's consider the second case. Let's prove that delta G will always be positive at any temperature if delta H is positive and if delta S is negative. So using the same equation, delta H is still positive 10 minus, let's try a high temperature, so let's plug in 1,000, and delta S is negative, so we're going to plug in negative 0.1. So 1,000 times 0.1 is 100, but because we have two negative signs, it's going to be plus 100. So we get positive 110. So we can see delta G is positive at high temperatures. So now let's try it at low temperatures. So using the same equation, H is going to be positive 10, and now we're going to plug in a low temperature value of 10, and S is still negative 0.1. So this is going to be 10 plus 1. 10 times 0.1 is 1. So we get positive 11. So as you can see, it's positive under low and high temperature conditions. So we could say it's positive or non-spontaneous at any or at all temperature conditions. So now let's confirm the third scenario when they're both negative. So this time we're going to plug in negative 10 for delta H. And it's supposed to be true at low temperatures, but let's start with a high temperature value. So delta H minus T, so let's plug in 1,000, a high temperature value for T, times negative 0.1. So that's negative 10, and then negative 1,000 times negative 0.1, that's positive 100. So that's 90, which is positive. So we can see that delta G is positive at high temperatures. We need to confirm that it's negative under low temperature conditions. So notice that it didn't say all. So on the table, because it says negative at low temperature conditions, that means that it's positive at high temperature conditions. It's the opposite. So now, let's try a low temperature. So delta G is equal to delta H, which is negative 10 minus a low temperature of 10 times negative 0.1. So this is negative 10. Negative 10 times negative 0.1, that's going to be positive 1. So overall, that's negative 9. So as you can see, it's negative only at low temperature conditions and not at high temperature conditions. So now let's look at the last case. So it has to be true at any temperature. So let's start with a low temperature. So H is going to be negative 10 and then minus T. So we're going to try a low temperature of 10 times entropy is positive, so we're going to plug in 0.1. So negative 10 and negative 10 times positive 0.1, that's negative 1, so we get negative 11. So as we can see, it's negative under low temperature conditions. Under high temperature conditions, let's plug in 1,000. This is going to be negative 10 minus 100, which is negative 110. And it's still negative under high temperature conditions. So when enthalpy is negative and the change in entropy is positive, delta G is negative at any temperature, because two negatives, when you add them, will always be a negative. But for this problem, B is the right answer. So the reaction will be spontaneous at all temperatures when enthalpy is negative and entropy is positive. 35. The equilibrium constant K is 1.83 times 10 to the negative 12 for a particular reaction at 372 Kelvin. Calculate the change in Gibbs free energy for this reaction. Is this reaction spontaneous at this temperature? So the equation that you need to find delta G using K is this. Delta G is equal to negative RT ln K. So R, you don't want to use the value 0.08206 for R. That's for gases. Rather, you want to use the energy constant, negative 8.3145. And for that value, R has the units joules per mole per Kelvin. So I'm going to write that in red. So joules per mole times Kelvin. And the temperature is going to be in Kelvin, so 372 Kelvin. So the units Kelvin cancel. So initially, this equation is going to give you the units joules per mole. So we're going to have to convert that to kilojoules. And then times the natural log of the value of K, which is 1.83 times 10 to the negative 12. So if you type that in, you should get 83,593 joules per mole. Now we wish to convert that to kilojoules, so we need to divide it by 1,000. So if we can also move the decimal 3 units to the left. So it's going to be 83.6 kilojoules per mole. And it's positive. So D is the right answer. Whenever delta G is positive, you have a non-spontaneous reaction. So let's review something. When K is significantly greater than 1, let's say like 10,000, delta G is going to be negative, and therefore it's going to be a spontaneous event. It's product favored. So the reaction proceeds as written. It goes from left to right. When K is significantly smaller than 1, like 0.0001 or like 10 to the negative 8, if it's very close to 0, delta G will be positive, and therefore it's going to be non-spontaneous in the direction that is written. So as it goes from left to right, it's non-spontaneous. And if K is approximately 1, typically delta G is approximately 0, and the system is at equilibrium. So those are some things that you want to keep in mind. So when K is significantly larger than 1, it's product favored. And whenever it's product favored, that means you have the reaction it's spontaneous, so to speak. And when it's reactant favored, it's non-spontaneous for the most part. So those are some concepts that you want to keep in mind. 36. Which of the following statements is/are correct? Is it A, B, C, or D? So these are some things you need to know. Oxidation occurs at the anode and not the cathode. So 1 is a true statement and 3 is a false statement. Reduction occurs at the cathode and not the anode. So number 4 is a true statement and 2 is false. So therefore the answer is A, 1 and 4. Oxidation always occurs at the anode. Reduction occurs at the cathode. And keep in mind, whenever the oxidation number of an element increases, it's oxidation. If the oxidation number decreases, it's reduction. And whenever an atom loses electrons, the oxidation will go up and it's oxidized. Reduction involves the gain of electrons. Oxidation is associated with the loss of electrons. So those are just a few things that you want to remember for electrochem. 37. What is the coefficient of zinc when the following redox reaction, which occurs in acidic conditions, is balanced? So what we need to do in this problem is that we need to separate it into half reactions. So let's start with zinc. Elemental zinc in its natural form or natural state has an oxidation state of 0. And it's going to become zinc plus 2, which has an oxidation state of 2. So once we balance the particles, we need to balance the charge. We have a total charge of 0 on the left and plus 2 on the right. So how many electrons do we need to add? The difference of 0 and 2 is 2, so we got to add 2 electrons. And you should always add it to the side with the higher charge, or the higher oxidation state. So we're going to add 2 electrons to the right side. So if we add up all the charges on the right, plus 2 and 2 times negative 1, which is negative 2, positive 2 and negative 2 adds up to 0, which is equal to the net charge on the left. So the charges are balanced. This half reaction is known as an oxidation half reaction because the oxidation state was increased from 0 to plus 2. Also, there was a loss of 2 electrons. Whenever the electrons are on the right side, it's an oxidation half reaction. If the electrons are on the left side, it's a reduction half reaction. So now let's balance the other half reaction. So we have bromite converting into bromide. So the bromine atoms are balanced. So we need to add 2 oxygen atoms. Under acidic conditions, you can add H plus and H2O to balance the reaction. So since we have 2 oxygen atoms on the left side, we need to add 2 H2O molecules on the right side so that the number of oxygen atoms are balanced. Notice that we have 4 hydrogen atoms on the right side. So we need to add 4 H plus ions on the left. Now the last thing we need to do is balance the charges. The net charge on the right side is minus 1, and the net charge on the left side is 4 times 1, which is plus 4, plus the negative charge, so plus 3. So what is the difference between 3 and negative 1? If you subtract 3 minus negative 1, that's like 3 plus 1, so that's 4. So we need to add 4 electrons to the left side. If you add up all the charges, negative 4 plus negative 1 has a net charge of negative 1. So the charges are balanced. The charges on the left side is now equal to the right side. So to get the net reaction, the electrons must be equal. Since they're not, we need to multiply the first equation by 2. So this is going to be 2, 2, and this is going to change to a 4. So now we can add up the reactions. So the electrons will cancel because we have 4 electrons on both sides. And we can bring everything down. So we have 2 zinc atoms. Let me change the color. Plus 4 H plus ions. Plus 1 bromide ion, which will convert to 2 zinc plus 2 ions, 1 bromide ion, and 2 water molecules. So as you can see, this reaction is balanced. We have 4 hydrogen atoms on both sides, 1 bromine atom, 2 oxygen atoms, and 2 zinc atoms on both sides. And if we look at the charges, we have plus 4, minus 1, plus 4 minus 1. So the charges are the same, so the net reaction is balanced. So now let's look at the question. They wanted to know what is the coefficient of zinc when the redox reaction is balanced. So we have a 2 in front of zinc. Now we could have seen that here. We didn't really need to add the two reactions to get the net reaction, but I wanted to do it for the sake of practice. So the coefficient is 2, so B is the right answer for this problem. So that's it. 38. Which of the following statements are true? 1 is a true statement. Whenever the cell potential is greater than 0, or if it's equal to a positive number, the reaction is spontaneous. 2 is false. If it's less than 0, it should be non-spontaneous. And 3 is true. If the cell potential is equal to 0, then the system is at equilibrium. So the correct answer for this problem is 1 and 3. So C is the right answer. So those are just some facts that you have to commit to memory. 39. Calculate the cell potential of a reaction if the change in Gibbs free energy is negative 41.3 kilojoules per mole and N has a value of 2. The equation that you need for this problem is this. Delta G is equal to negative NFE. Now delta G has to be in joules per mole, not kilojoules per mole. So we need to multiply this value by 1,000. So we're going to plug in negative 41,300 joules per mole. N has a value of 2. F is Faraday's constant, which is 96,485 coulombs per mole of electrons. So let's solve for E. So if we multiply 2 by 96,485, we should get 192,970. So let's divide both sides by negative 192,970. So these cancel, and therefore the cell potential of this reaction is positive 0.214. The two negative signs cancel. So C is the right answer. Now keep in mind, when delta G is negative, we said it's spontaneous. And when E is positive, it's also spontaneous. The reason why the signs are opposite is due to the negative sign in the equation. Number 40. Calculate the cell potential of the reaction using the information shown below at 298 Kelvin under non-standard concentration values. So we have the standard cell potential, which is the cell potential if the concentration of the reactant and the product is 1 molar. However, we want to find the cell potential when the concentration of aluminum is not 1 molar, it's 1.5 times 10 to the minus 5. And when the concentration of the copper plus 2 ion is about 35.4. Now, notice that the concentration of the product ion was decreased. The standard value is 1, but it was decreased to 1.5 times 10 to the minus 5. Now, whenever the reaction shifts to the right, the cell potential will increase. And whenever it shifts to the left, the cell potential will decrease. So, since we decrease the concentration of the product, will the reaction shift to the left or to the right? According to the Chatelier's principle, if you decrease the concentration of the product, it's going to shift to the right to increase the concentration of the product. And because it shifts to the right, the cell potential should go up. Now, for the reactant, the copper plus 2 ion, we've increased the concentration of the reactant, so it should shift to the right, and the cell potential should increase as well. So the cell potential at these concentrations should be greater than 2 volts. So what this means is that we could eliminate answer choice A and answer choice B. Now the equation that we need, the non-standard cell potential is equal to the standard cell potential value minus RT divided by NF, natural log of the reaction quotient Q. The reaction quotient is the ratio of products to reactants. It's very similar to K, but it's associated with initial concentration values. So Q is the ratio of the aluminum plus 3 ion squared over Cu plus 2 raised to the third power. The coefficients turn into exponents. Now the next thing we need to know is the value of N. If we write out the half reactions, we have 2 aluminum atoms turning into 2 Al plus 3 ions. And so to balance it, we need 6 electrons. And then for the other half reaction, where we have 3 copper plus 2 ions turning into 3 copper atoms, we also need 6 electrons to balance it. So therefore N is equal to 6. So now let's plug everything into the equation. So E is 2 volts. R is the energy constant, 8.3145. For gases, it's 0.08206. The temperature is 298 Kelvin. N is 6. Faraday's constant is 96,485. And then times the natural log. So for aluminum, which is the product ion, it's 1.5 times 10 to the minus 5 raised to the second power. By the way, we can't include the solid copper or the solid aluminum because liquids and solids should not be included in the equilibrium expression or in the reaction quotient, just in case you were wondering. Now, the copper plus 2 ion concentration is 35.4, but we have to raise that to the third power. And all of this is inside the natural log. So if you type this information into your calculator, you should get answer choice E, 2.14 volts. Now, if you prefer to type it in one at a time, here's what you get. Let's multiply 8.3145 by 298. So that's going to be 2477.7. And then 6 times 96,045. That's 578,910. And then the natural log of 1.5 times 10 to the minus 5 squared divided by 35.4 raised to the third power. That is going to equal negative 32.915. So negative 32.915 times negative 2477.7, that's 81,553, and then divide that by 578,910. You're going to get positive 0.14. So what we have now is, this is going to be 2 plus 0.14, which will give you 2.14. So D is the correct answer.